Here we have a quadrilateral GOAT that is circumscribed by circle P. So you can see the quadrilateral here, and it's circumscribed, meaning all the points are going to be extended as far as they can in the circle. They're all points on the circle. So we're given that side OG is congruent to side OA. So that's shown here with these lines, right? You can see this line and this line signify they have the same length, right? They're congruent sides. And then the measure of angle O, which is this angle up here, is 62 degrees. So let me just label that on there. And the measure of arc AT, that's a minor arc AT, is 40 degrees. I know it's minor because it's less than 180, and generally that's like what you would assume, right? The major arc would go the other way, that'd be 320 degrees. But so this minor arc AT has an angle measure of 40 degrees. We need to fill in the measures of the inscribed angles. Inscribed angles will be angles that start from a point on the circle, extend to a point on the circle, and then extend back to another point on the circle. So for instance, OGA, this angle here would be an inscribed angle. It's extended as far as it can. We need to find the central angles. Those are angles that use the center as one of the points, so like OPA. And minor arcs like AT or OA, it's a section of the circumference that's less than 180 degrees, less than half the circle. So we need to find these angles here and these arcs. Even though the arcs are over on the right side, I would start with those arcs because we already have AT, and because we know that this OG is congruent to this OA, we can extend GA over and we make an isosceles triangle. We know it's isosceles because they have the two congruent sides, which means that the opposite angles are also going to be congruent. So angle OGA is congruent to angle OAG. Now, since we have the 62 degrees and we know that all triangles will have the angles add up to 180 degrees, we can figure out what those two angles are. We can essentially say 62 plus measure of angle OGA plus the measure of angle OAG, which is the same thing. So essentially we could do 2 times the measure of OGA would add up to 180 degrees. So now we can just subtract 62 from both sides, and that will give us that 2 times the measure of angle OGA equals 180 minus 62 would give us 118 degrees. Now to solve for just the measure of OGA, we would divide both sides by 2, giving us that the measure of angle OGA is 59 degrees. And since we know that OAG is congruent to that, OAG is also 59 degrees. Now with those angles, we can figure out what the measures of the arcs are, because the measure of the arc is always equal to the measure of the central angle, and both of them are always going to be double the inscribed angle that captures that same angle. Right? So OA is captured by this OGA. So that means that OA is going to be double. Again, this inscribed angle, double 59 would be 118 degrees. So now we could do the same thing for OG using the 59 over here, but we can also take advantage of the fact that they have the same length chord. Right? So OG is the same length as OA, and if you have the same length chord on the same circle, then that means they're going to capture the same measure of arc and the same length of arc. So the fact that arc OA is equal to 118 degrees means that arc OG must also be 118 degrees. All right, so again, that's 2 different ways you could do that. You could use the 59, or you can, once you have one of them, you can figure out what the other one is. So we said arc OA is 118 degrees. Arc OG is also 118 degrees. And now we know that the entire circle will have an angle measure of 360 degrees. If we went all the way around, it would be 360. We have this 118, we have this 118, we have this 40. We're just missing the GT. So we could add all of those up. We could say 118 degrees plus 118 degrees plus this arc TA is 40 degrees plus the measure of arc GT here would have to be equal to 360 degrees. So if we add those up, that would give us 236 plus 40, which would be 276 degrees, plus the measure of arc GT, adds up to 360. We could subtract 276 from both sides, giving us that the measure of arc GT, minor arc GT, is equal to 360 minus 276, which will be 84 degrees. We can label it on the diagram right there. So now we've got all of these minor arcs going around. They ask for this other minor arc TAO, which will be a combination of arc TA and arc OA, or AO. So all we have to do is add that 40 with this 118, which will give us 158 degrees for the measure of arc tau. Right, now that we have these minor arcs, it makes it much easier to find all of the angles that they're asking for. So say we start with the angle A here. Angle A is this entire thing, OAT. So that includes this 59 degrees and also this angle over here. And if we want to find that one, we can just use the arc that it captures. So GAT here captures this 84 degree minor arc. That doesn't mean that this angle is also 84 degrees. You can even look at it and say, okay, that's not nowhere close to 90, it's less than the 59. Assuming this is drawn somewhat to scale. But also we know that the inscribed angle will be half of the minor arc that it captures. So half of 84 would give us 42 degrees. So we have 59 degrees plus 42 degrees makes that angle A. And that will give us 101 degrees for the measure of angle A. Next we have the measure of angle T. So angle T captures from G all the way over to A. So GO and OA combined. Now, again, the inscribed angle will be half of that. So we can see that the measure of arc GO is 118, the measure of arc OA is also 118. So to find the total of those, we'd have to do 118 times 2, or we could just do 118 plus itself. But then because it's an inscribed angle, we have to divide by 2. So essentially, we're multiplying and dividing by 2. That will cancel out and just leave us with 118 degrees for the measure of angle T, which makes sense. It looks like it's a little bit above 90 degrees. Next, we have the measure of angle G. So G, like measure of angle A, includes a 59 degrees plus another snippet. It's not going to be 42 though. We have to figure this one out using the AT. So arc AT is 40, which means that the inscribed angle that captures that will be half of 40. Half of 40 would be 20 degrees. So we have 59 degrees plus 20 degrees, giving us that the measure of angle G is 79 degrees. All right, next we have OPA. Measure of angle OPA, that's going to be a central angle. Central angle is just equal to the measure of the arc that the central angle captures. So in this case, that would be arc OA, which is 118 degrees. Next, we have arc GPA. So that's from G to P to A here. So that includes these two arcs, AT and TG. So again, the central angle is equal to the measure of the arcs. So it would be 40 plus 84. And that gives us that the measure of angle GPA would be 124 degrees. All right, so that's how you can find all those angles. Once you have all of the 4 angles of the quadrilateral, you can also add them up to make sure they do add up to 360, which they do in this case. Anytime you're doing something with angles, just size up. The diagram is not necessarily drawn to scale, but make sure that it makes sense. Do the angles add up to what they're supposed to? Right? Do the arcs all add up to 360 if you have them going all the way around? Just make sure that something that should be somewhere near 90, that you end up getting something near 90, and maybe compare it. Is it supposed to be acute? Is it supposed to be obtuse? And it checks out. All right, next we have a circle with radius 6 centimeters, and the circle is inscribed. So the circle is inside of the hexagon as far as it can fit out. And the hexagon, LEBRON. What's the area of the purple region? So the purple region here is the area inside the hexagon, but outside of the circle. That means that to find the area of the purple, we're going to need to do the area of the hexagon minus the area of the circle, right? Because we want the entire hexagon, and then you take out the circle part that is not purple. So to find the area of the hexagon, similar to my previous video, what you need to do is start by breaking that hexagon up into triangles. And this only works because it's a regular hexagon that is given, meaning that all the sides are the same, all the internal angles are the same. Again, I didn't cut that perfectly, but this should be into 6 equal slices, 6 congruent triangles. And we need to find the base and the height to find the area of one of those triangles. Then we're going to multiply it by the number of triangles, in this case 6. We actually don't know what the lengths of these sides are. And those sides could help us find the base, in this case because it's a hexagon. Just for regular hexagons, it will be made up of 6 equilateral triangles. But we're going to ignore that, not use special right triangles. That's usually how I would solve a hexagon. But I'm going to show how you can solve this for any regular polygon, which would involve using trig. But in this case, these lengths are not 6 because the radius is 6. You can see that each of these lines, even if they were drawn perfectly, clearly I did not draw exactly straight lines going through them. But this is not a radius because it extends past the radius to the point beyond that radius. So if we were to actually draw a radius, it would go from the center to the edge of that circle right there. And that radius we said is 6. So using that radius, we would say that is called the apothem. An apothem is just a radius of a circle inscribed in a polygon or in a shape where it's going to pass through the midpoint or touch the midpoint of one of the sides of that polygon. So in this case, for the triangles that we make, the apothem will be the height of that triangle. If we redraw it right here, we've got 6. And then we break that up into a right triangle. So we can find the base using our trig functions. The entire base would be like the side here, right? It would be one of the sides of the triangle. We can use trig to find half of that base because right, we break it up into two equal right triangles. Again, that only works that you can break it into two right triangles because we know it's at least an isosceles triangle. So an isosceles triangle, when you drop an altitude, the altitude will cut it in half. So if we use trig functions, we're going to be using the opposite of this angle up here. And to find that angle, we would just do 360 degrees. That's the entire circle going around, divided by the number of slices. That's the number of triangles, which is 6. So each of these angles up top is 60 degrees, which means when you cut it in half, you'll get 30 and 30. So again, that's why you could use special right triangles in the case of hexagons. Normally that's how I would do it, but I'm just going to show how to do it with trig function. So even if you didn't have a 30, 60, 90, you could follow these same steps. We have opposite is the base over 2 and the adjacent is 6. Opposite and adjacent uses tangent. Tangent is TOA. So the tangent of 30 degrees is equal to the base over 2, right, half of the base, divided by the adjacent, which is, again, the apothem, 6. Now, to get the base alone, you're going to have to multiply by 6 and then multiply by 2 to get rid of that, divide by 2 because it's half the base. So I'm just going to multiply both sides by 12. That's the same as multiplying by 6 and 2. And that gives us that the base is equal to 12 times the tangent of 30 degrees. And make sure you're in degree mode when you type that in. I'm going to leave the base in terms of tangent until the end so that I don't round until the end. You can also round and just go beyond what you need. And then, again, always save your rounding for the end of the question. We have already that the height is the apothem, so that's 6. So if you want to find the area of one triangle out of the 6 triangles here, that would be equal to the base times the height over 2, or 1/2 base height. In this case, the base is 12 tangent of 30 degrees. Our height is 6. We divide that by 2. So we have 12 times 6 divided by 2. That ends up being 6 times 6 is 36 times the tangent of 30 degrees. Is, again, not our answer. That's the area of the triangle. Now, using the area of the triangle, we can find the area of the hexagon because the hexagon is made up of 6 of those congruent triangles. So we just do 6 times, and then the area of the triangle, which is equal to 6 times 36 tangent of 30 degrees, which will give us 6 times 36 is 6 cubed, is 216 times the tangent of 30 degrees. All right, so now we have the area of the hexagon. If we want to find the area of the circle, because that's what we're going to have to subtract from the hexagon, we know that the area of a circle is equal to pi times the radius squared. In this case, the radius is 6, so that means we'll end up with 36 times pi. All right, so we're using this and we're using this to plug into our area of purple equation that we wrote at the beginning. So the area of the purple is equal to 216 times the tangent of 30 degrees minus the area of the circle, which is 36 pi. Now again, I'm not rounding any of those things until the end. I'm going to type this in exactly as it appears there on my calculator. So 216 times the tangent of 30 degrees, make sure you're in degree mode, minus 36 pi gives me 11.61032262. Now, I didn't specify at the beginning, but say we were rounding to the nearest hundredth, then we would say it's 11.61. Our units were centimeters. So for area, it's going to be centimeters squared. Which makes sense. It seems like a small number, but if you think about the purple region is actually pretty small because most of the area inside of the hexagon is also overlapping with the area of the circle. So we're only left with that 11.61. All right, next we have regular pentagon, JAMES, and it is circumscribed by a circle as shown. So in this case, the pentagon is inside of the circle. The circle is the thing that's outside. If the circle has a radius of 23 meters, what's the area of the pentagon? All right, so first let's draw our triangles because we know if we need to find the area of the pentagon, in this case, we're not finding an area outside or anything fancy like this last one where we find the area of the purple region. We just need the area of the pentagon. We know we're going to ultimately need to divide it up into congruent triangles. This again will work because it's a regular pentagon. Otherwise, those triangles would be different sizes and this would not work. Okay, so again, didn't draw it perfectly there, but we've got our 5, what should be congruent triangles. And then we've got 23 is going to be our radius. In this case, the radii do extend from the center to the vertices of the polygon. So that seems like it will be helpful, except in this case, it's not an equilateral triangle. So the fact that these are both 23, it's isosceles, the base is not going to be 23. Now, where that will help us is when we redraw that triangle and divide it into 2 right triangles, the 23 will be the hypotenuse of the right triangle there, or the hypotenuses of both of them. All right, so we have that 23. And we can also find the angle, right? Again, the entire circle is 360 degrees. If you divide it into 5 equal sized slices, you just divide that by 5, gives us 72 degrees. So each of these angles up top is 72 degrees. And then because it's an isosceles triangle, right, we have 23 and 23, when you cut that in half with an altitude, or when you drop an altitude, it will cut that angle in half. Half of 72 would be 36 degrees. All right, so now we have 36 degrees up top. And in this case, I know in my previous video I said when you're finding the area of a polygon, generally you're going to be using tangent, because if they gave you the base, you need tangent to find the height. If they gave you the height, right, the apothem, then you need to use tangent to find the base. In this case, they're giving us the hypotenuse. So we're going to have to do 2 different trig functions to find the base and the height, but both of them will not be tangent. We're going to have sine to get one of them because the opposite is this half of the base here. Right, we know the entire base would go all the way over, but this is base over 2. And our height is going to be using cosine, right? That's adjacent over hypotenuse. So we're going to use those 2 functions. Again, sine of 36 degrees, that's the angle up top, is equal to opposite, which is half of the base, over hypotenuse. So base over 2 over 23, which means to get the base alone, we need to multiply by 23 and multiply by 2. That's the same as multiplying by 46. Right, that's double 23. So that gives us that the base is equal to 46 times the sine of 36 degrees. So we have the base again. I'm going to leave it like that until the end. Now if we want to find the height is adjacent to 36. So we're going to use cosine. So the cosine of 36 degrees is equal to adjacent is height divided by our hypotenuse is 23. To get the height alone, we just multiply both sides by 23, leaving us with the height is equal to 23 times the cosine of 36 degrees. Right. Now to find the area of the pentagon, we're just going to do 5 times the area of one of those congruent triangles. And to find the area of one of those triangles, we would do 1/2 times base times height, or base times height over 2 is an equivalent expression. So we would do, in this case, 1/2 times our base was 46 times the sine of 36 degrees, times our height, which is 23 times the cosine of 36 degrees. Okay, I'm not going to round those until the end here. That would give us 1/2 times 46 is 23. So we have 23 times 23 is 23 squared, which is 529, times sine of 36 degrees, times the cosine of 36 degrees. Again, this is not our answer. This is the area of just the triangle. We're trying to find the area of the pentagon, right? Area of the pentagon. So that would be 5 times the same thing that we just wrote. Paste. So 5 times 529 sine 36. Right, and we can type that into our calculator exactly as it is there. I don't even need to do 5 times 529 first. 5 times 529 times the sine of 36 degrees, make sure you're in degree mode, times the cosine of 36 degrees, gives us the area of the pentagon is equal to 1,257.772243. If we were to round that to the nearest hundredth, that would be 1257.77. Our units were in meters, so this would be meters squared for the area. And if you want to just quickly check, does that number make sense? Because it seems like a really big number. Find the area of the circle, right? The area of the circle would be pi times 23 squared, right? Our radius is 23. 23 squared is 529. So 529 times pi, even without multiplying that out, we know pi is more than 3. 529 is more than 500. 500 times 3 is 1,500. So the area of the entire circle would be more than 1,500. So, this is smaller than 1,500, but it's also in somewhat that ballpark. But if we take out these big purple chunks, that number does seem like it could make sense. So that doesn't tell us we're definitely right, but it allows us to know we can't immediately rule this answer out, that it doesn't make sense. Right, so that would be how you would do those. Make sure that you're following the steps whenever you're finding the area of a polygon. Divide it into triangles, find your base, find your height, find the area of one triangle, and then multiply by the number of triangles. Going back to the beginning, again, it probably helps to find the minor arcs first. We know that the minor arcs will have the same angle as the central angle that captures them, and the inscribed angles will always be half of the central angle, half of the minor arc. So use all of these tricks and just make sure for any time you have a shape inscribed inside of another shape, especially if one of those shapes is a circle, think how you can connect those shapes. So in this case, our radius was the height of the triangle, right? It was our apothem. In this case, the radius was one of these hypotenuses of the right triangle, or one of the sides of the isosceles triangles we made.